Last time I was discussing about decoder. Decoder, there I have left you. Just continuing the same. Last time I was discussing about decoder. Decoder is a circuit that converts a binary number to decimal number. There was simple program for that, and this was this program. It was 2 to 4 decoder. It was accepting input as a vector in the vector form, and it was providing you output in the vector form. So yesterday, as it was discussed, this was discussed that how you will program this type of combination circuit is accepting 2 input and is providing you 4 output. So here, this was discussed with the help of component and with the help of vector type of input. So today, continuing the same lecture, we will discuss about mux and demux coding. So before that, let us see how it was programmed. It was uh, it was decoder 24. 24 means 2 into 4 decoder. It was accepting A in STT logic vector 1 down to 0. 1 down to 0 means it is of 2 bit. 1 down to 0, means it is of 2 bit. Y is out STT vector 3 down to 0. 3 down to 0 means it has 4 output. It has 4 output. So 4 output means it is accepting 2 input and providing you 4 output. That's why it is 2 is to 4 decoder. So architecture was like that. Uh, when see basically this is the suppose this is decoder here. It is accepting 2 input and is providing you 4 output. Let it is A, it is B, it is Y0, it is Y1, it is Y2, and it is Y3. Now, if I will program it, so condition is that A, B, and it is Y0, Y1, Y2, and Y3. Now, let us see. So here, suppose when it is 0, then Y0 will be active. When it is 0 1, 0 1 means bind if input is 0 1, so output will be 1 there. When input is 1 0 1 0, that means in binary format input is 1 0, so output will be 2 here. When input is 1 1, that is in the binary format input is 1 1, output will be 0 0 0 1. Y3 is active. Using the same logic, we have tried to design this. So Here it is written that y0 is L and M. See, input is here, A is the input, that is of 2 bit, A of 0 and A of 1. A of 0 and A of 1 means 1 minute, just wait. Suppose I am writing A, that is in bit vector 2 down to 0, 2 down to 0. It means A is actually A of 1 and A of 0. It is of 2 bit. 2 down to 0, sorry, 1 down to 0. 1 down to 0 means it is of 2 bit. That is 1 and 0. Suppose it is 2 down to 0. 2 down to 0 means it is of 3 bit, 2, 0, 1. So it is A2 into A1 into A of 0. So this is the technique that is used here. Suppose why I'm saying y is out bit, not out std logic, out underscore std underscore logic, and it is logic underscore vector to have in the array form 3 down to 0. 3 down to 0 means it is of 4 bit, means actually y is y of 3 into y of 2 into y of 1 into y of 0. Bit at position LSB is y of 0, bit at MSB position is y of 3, and in between is y of 2 and y of 1. So in this way, you will write uh, the inputs in the vector form. That's why it is written as L is less than equal to not A and not B. Why it is written? Actually, it is see, to get y0, it should be y of 0, that is this one. It should be not A and not B, not A and not B. Similarly, y1 is A, not A, B. Y2 is A, B complement, and Y3 is A, B. Y3 is A, B. So altogether, you need to code these. That's why it is coded as not A and not B. It is uh, calculated using not, that is L is less than equal to not A. L and M are the intermediates. That's why it has been used as signal here. These are steady logic. It has been calculated, and then y0, y1, y2, y3 has been calculated here, and thus you will simulate this. Similarly, it was discussed yesterday that how you will use component part. That is, yes, component part. How we will use? How you will use? like this three input AND gate is has been programmed here, and you need to have one circuit. You need to have one circuit like this. Circuit is you need to have one circuit. Let You need to have one circuit, and circuit is like this. There are three AND gate. It is accepting, suppose it is accepting a L M N. It is PQR. It is X Y Z. Suppose these are the three input. These are AND gate. I'm making it cross here. These are AND gate. Output of these three AND gates are acting as input to one OR gate. It is acting to input of one OR gate, and you are getting Y. You are getting not, it should not be Y, since Y has been taken as input here. Let us rename at Y1. Okay. Y1 is output, and these there are altogether 9 inputs, and it is providing you one output. There was need of this circuit. Now you can see here, this cross is actually indicating 3 input AND gate. So here 3 input AND gate means 3 input AND gate means it is accepting 3 input and providing you one output, and multiple times same gate has been repeated 3 times. One 3 input AND gate is repeated, and in the library only 2 input AND gate is defined. So we need to design one AND gate of 3 input, and that will be called 3 times. So this was the need yesterday. So it was discussed like this. At first, we have coded for 3 input AND gate, entity and underscore 3, and using IEEE library, I have programmed this. So we have programmed this. It is entity underscore and 3. It is accepting 3 input and providing you one output. So and our entity, then is architecture data flow and underscore 3. It is giving you A and B, and the output of A and B is stored in D. D is intermediate, and then D and C is giving you Y. So Y is actually the end of A, B, and C. To get the end of A, B, and C, you have used a signal D. We have used a signal D here. Now, again, library. Now the same function will be called 3 times as per the required condition. Here condition is that you need to draw, see, you need to draw this circuit. You need to draw this circuit. So let us draw it. See, in the next program, we are just programming for the given circuit. It is library IEEE use IEEE ST logic 1164.all. Then entity circuit is it is accepting the types of input it is accepting. It is written as element PQR XYZ. It is in STD logic condition. Z1 is let Z1 is or Y1 is output out STD logic, then is an entity. Then see here, architecture of the same circuit is written here. Here, uh, end of these are actually these arrow, these 3 arrow. And since these 3 arrow are different signals, so it should be stored somewhere. Temporary, it should be stored somewhere. That means as an intermediate, it should be stored. That's why we have taken A1, A2, A3 as signals. This will be actually used to store these data, the output of these three gates, similar gates. That's why we have used this A1, A2, A3. Now component N underscore 3. See, initially we have defined this function. Whenever you are calling any function within the same program, you have to program it at first. And then if there is need to call that function, you have to consider the same entity as component. See, initially it is n under entity n underscore 3. I'm using the same thing as entity as component here. See, component n underscore 3 and its port is same. Entity will be used as component here now. That means you are calling, there is need of this type of gate that is actually not in the library. 3 input AND gate is not in the library. You are using this gate multiple time to get the architecture, to get the required architecture. That's why you have used component. You can match the inputs and as well as output. There must not be mismatch here. You have to take care that whichever function you want to call, its input and output and the name should match. It should match. So component and entity that you are using, that should match. So component n underscore 3 port and then n component. A, B, C is the input here. In the entity also, ABC is input and Y is output. Y is output. Now you have to take care also that the alphabets that are used in the component, the alphabets that are being used in the component, try to avoid using those alphabets at other instance of program. So see here that you have to take care, else it will show error. Now, how to use this component? See, signal, after that component is written, then is began. You have to learn this sequence also, that before begin, signal is written, before begin, component details will be written. If you are taking some variable, then it is written after begin, then after begin, again begin is written. Here, you have to learn that after architecture, you can write signal, but signal should be before begin, and component is also written before begin. You can interchange this sequence also. Component is taken first, signal is taken second. Yeah, it is accepted. There is no error. It is not a syntax error, but before begin, this should be used. It should be used before begin. Actually, signals are the global signal. A signal that is used here may be used else within the same program. That's why it should be out of the loop of begin. The statements that are written between begin and end architecture, these are actually sequential statements. You should take care of this. Now see how this statement is written. To use any component, at first you have to initialize it. You have to take any arbitrary value starting from alphabet. This L1, L2, L3, actually these are not syntax, as their font color is not red. You better understand that if it is not in red color, means it is not a syntax. That is logical. You can write anything here, but should start with alphabet. So I have initialized this L1 colon. Just you have to learn this pattern. L1 colon n underscore 3. Actually, the component that you are calling, the function that you are calling multiple time, n underscore 3. Then it is written port map. Actually, what does it mean? It means that this is a AND gate. It has three input. It has three input, and these are open socket. These are open socket. At these socket, what you are feeding? Actually, you are using this as a component in the program. You are using this as a component, and at these are actually open socket. At this open circuit, what you are using? You are using charger, you are using laptop charger, you are using mobile charger, you are using this socket to light a bulb. What for what purpose? Actually, this socket is for general purpose. It can be used at multiple points. Same in the same way, the AND gate that has been programmed above, that AND gate is used here, that AND gate is used here, and whose port map is to be written. That means at ABC, uh, this component at ABC, these are the three inputs A, B, and C. At this position, which new input is applied? I'm saying it is PQR. So applying here P, Q, and R. So applying here PQR, I'm getting, let it is PQR, PQ, and R. So PQ and R is giving you, it is stored in, suppose A1. It is stored in A1. It is stored in A1. So I've written A1, PQR is and is stored in A1. See, without writing program, you are using this N underscore 3. Similarly, LMN, it is accepted in 3 input AND gate, and its output is stored in A2. And XYZ, it is stored in A3. These are three are odd, and it is stored in Y1. It is stored in Y1. So you can see A1 and or A2. A1 and or A2. These are two odd, and output of this is odd with A3. So you are getting the output, and output is stored in Y1. Now let us save this. Saving it and then compile it. Yes, there is no error. Just after that, you can simulate. Now let us start the new program. That is how you will use mux, how you will code mux. So see here, mux. The basic thing behind this mux, you should know what is the actual architecture of mux. That should be known with you. How mux is used. What type of selection inputs are available. If it is 2 cross 1 mux, how many inputs and how many outputs, that should be known to you. So let us take 1 mux that has 2 input, and it is providing you 1 output. So it is 2 cross 1 mux. Then definitely 2 cross 1 mux, since it is 2 to the power 1. So 2 to the power 1 means this is the selection input. There will be one selection input, and it will provide you one output. So there will be one output here. So considering the same, let us see how it will be programmed. Suppose this is S, this is A, and this is B. So S is obtained, Y is written as, in terms of AB, Y is written as A. If it is at 0 position, it is at 1 position. Then it will be written as A into S plus B into S complement. Directly you can program this. So 2 cross 1, you can write it here as we will try to see here how if else condition is used in the same program. Similar simple program, how you can write, how you can use if else condition, how you can use process statement here. We will try to learn this. Entity mux, that is 2:1, is port map. We should have figure also here. Port. See, it is accepting two input. It has two inputs as well as one selection input. These are all are acting as in std underscore logic. Then is colon, and then is y is output, y out bit, out std underscore logic. Fine. So colon it, and then is end entity. And entity colon close, then architecture mux 21 data flow of mux 2 cross 1 each. See, we are knowing that how y is obtained. Directly you can write function begin y less than equal to, there is need of s in normal s and not s. So you can write a and s, or b and not s. B and not s, and then close it with colon, and then end architecture. End architecture, enter it. Now let us see, is there any error or not? See, there is no error. It is mux VHD is successful. Now let us see how compiler is working. Here, we should know that when S is 1, that will understand when S is 1, when S is 1 here, this is S and this is Y. When S is 0, Y is equal to B. When S is 1, Y is equal to A. Means whatever B is, that is reflected to Y when S is 0. Whatever A is, that is reflected to Y when S is 1. So A and B are available. Let us compile it. Let us simulate. We have to search for the name, that is mux2. See, it is mux21. So mux21, okay. Then instant Here you have to add to wave all items in the region. All items in the region C, A, B, and S were acting as input. Let us take A as one clock, so that we will try to see whether A is reflected to Y or not when S is something. So it is, let us take it is as 100 PS, 100 PS, and let us take B as 50 PS, 50 PS. Let S is taken as 1. Let's take it as 0. 0 means, 0 means it will be selected. It is going to select 0 means B will be reflected. 0 means B will be reflected at Y. Let us see here, is it going out not? I have fed it all the data. Now let us see. See, initially S is 0. Initially S is 0. S is 0. Then at 0, we have created functions such that at S equals to 0, Y is equal to B. So see here, B is the second wave. The second wave, try to match B with Y. See, every time it is matching, it is not matching with A. A, frequency of A and frequency of output, they are different. However, frequency of B and frequency of Y, both are matching. Both are matching. The second and last, the second and fourth wave, you can match it. They are always matching. Means B is directed to Y for S equals to 0. Now let us see when S is 1. When S is 1, what is happening? Now try to see when S is 1, the upper wave and the last wave. First and fourth row, first and fourth wave, you can match it. They are just a replica of each other. It says that when S is 1, A is equal to Y. That is, Y is equal to A. Y is equal to A for S equals to 1. And if you are combining both, let me unzoom it. So in this way, we have understood how you will code 2 cross 1 mux. Let us use if-else condition in the same program. Ending the simulation, let us see how you will simulate the same program using if-else condition. To use if-else condition, you have to use one thing here, that is process. For process command, you need to use clock here. If else condition will be used here. Here to use if else condition, you need to understand how you will use process statement. How you will use process statement. Actually, this time, whenever you are using process statement, uh, that time, actually, we are discussing about behavioral style. behavioral style of architecture. Till now, we have discussed data flow and structural style. Now, today we will try to cover how we will write the same program using process. So let us mux b, that is behavior. See here, we have okay, fine architecture. Begin, and then we will write here process. See, process is a statement. Whatever is written inside this alpha, this parenthesis, they are case sensitive. They are sensitive means whenever event will occur on them, output will be affected, or there will be event on the output. When there is no event on these mentioned inputs, output will not be affected. So here begin if s equal to 0, then y less than equal to a, colon, y less than is equal to a, sorry, b, else, since there are only two statements, so if else will not be used. One if and else, only two statements will be used. Else you have to mention the condition also, then y less than equal to a, colon close. Then you have to end if, you have to end process, and then end architecture. In this way, you will use if else here. We will try to discuss if more than two conditions are used, how if else condition are used, how while condition will be used. That will be discussed in full class 1 bucks. We'll try to cover the same thing today. So see here, s equals to 0, then y is less than equal to b. And when s equals to 1, then y is less than equal to a. Process statement has been used. Here A, B, and S is written. Since event is taking A, B, and C, actually input are A and B. These are available second. S is the input here. So whenever event are taking place at A, B, and S, output should be affected. Output should be affected. That's why see here, S is included in process. It is written here also. Is saying there is error here. Process begin. Yes, now mux B is successful now. Actually, there was error here since if condition is written that is s is equal to 0, then by default else is s equals to 1. That's why no need to write then y is less than equal to a. If s equals to 0, then y is b, else y is a. Means other than s equals to 0, y will be a. Other than s equals to 0, since s is in STD logic, means it is accepting only bit type. So if one value is 0, other value will be definitely 1. So you can program the same thing, same mux using this statement, if else statement. Similarly, we can have this program also like mux 2, as I have discussed in this way also. When a equals to y less than equals to a, when selection is 0, else b, else b. The same statement can be written in this form also, or in this form also. Process, it is written as I0, I1 selection input. These three are taken within the process as it is discussed in the program. These all three A, B, and S, A, B, and S are taken within the process form, and then S is written, and whatever is written within this parenthesis, these are sensitive elements. Sensitive elements means whenever event will occur on any of these, output will be affected. If there is no event on this, it will be not visible at Y. It will be not visible at Y. Let us see. Suppose I am removing S from this position. S from this position, if it is removed, even it is saying successful, but when you will simulate, there will be error. Since S is not in the process statement, S is not within this parenthesis, within the process parenthesis, it is not going to be included. Effect of changes in S will not be reflected on Y. That's why to track these, you have to keep all the inputs here within the process state. That you have to take care. This is the part of behavioral. This will be helping you while you are designing counter, while you are designing register, while you are designing FSM. That time you need to mention sensitive input, sensitive signals. It may be of signal type, it may be of input type, maybe of input output type, like clock. So let us take other program, and that is a 4 cross 1 mux. 4 cross 1 mux using case statement. See here case statement, how case statement will be used. In the same way, suppose A, B, C, D are the inputs. And since there are 4 inputs, so 4 cross 1 mux is required. So there will be 2 selection input. We will try to use while if while statement or if else statement. So mux 4 4 1 4 1, that means it has 4 input. Let us take it as initial logic underscore vector 3 down to 0, 3 down to 0, means it has a 4 in. Since there is 4 input here, so if you're considering the selection input, how many selection input will be there? There is one mux here. It is accepting 4 input, that is 2 ki power 2 That's why this 2 is reflected here. That's why it has two input, two selection input. It is 4 cross 1 mux. It is providing you one output. So it has two selection input. Let us take it as S1, S0. So while taking S1, S0, you must know that that S1 is here, S0 is here, and Y is here, suppose. It is Y, I3, I2, I1, and I0, suppose. Now, when both selection input is 0, what is Y? When 0, 1, when 1, 1, 0, when 1, 1. So for 0, 0, I0 should be reflected. If this is at 0 position, this is at 1, this is at 2, this is at 3. So I0 is reflected here. Here, I1 is reflected. Here, I2 is reflected. And here, I3 is reflected. You need to write this coding. You need to write this coding. So see here, I have to program the same thing at this position. Begin. I have included input as a vector form and y as out vector. Let us take selection input as in std underscore logic in std logic underscore vector one down to zero. One down to zero, and y is out std logic vector, out std logic, and is colon and entity. It is mux 41 is, then is begin. Here process, within that I'm writing a comma s. Since there are multiple inputs, so it's better to use it, it's better to include all these in vector form. That's why it has been included in the vector form. S is in std logic underscore vector, one down to zero, and out is y. Since it is of one bit only, that's why y is out std logic. Process s, a comma s, input A is input and S is selection input. Fine. Then begin and then write if S equal to, since it is of 2 bit, since it is of 2 bit, here you can see S was of single bit, 1 bit. That's why single inverted comma is used. Here, double inverted comma will be used. That is 0, 0. Then Y. Y is of single bit, 1 bit. So Y is I of 0. Sorry, A is input. So Y is A of 0. As in the figure, it was said that when both are 0, 0 is reflected. 0 is reflected. Let us take it as I. Take it as I. And here also I'm just taking it as I. So it is I 0. Then closing the statement. Now see how else is written. Else if, it is not ELSE, it is else if more than two condition is used, then you have to write else, ELS. E is not written here. ELS if, else if S equal to, then is 0, 1, then Y less than equal to I of 1, as in the table. For 0 1, for 0 1, y is I1, colon close. Then else if, see, when I have written ELSE, it has not been taken as syntax. Now it is taking as syntax S equals to colon, and then is 1 0, then y less than equal to I of 2. Else if S equals to 1 1, then y less than equal to I of 3, colon close. Then end if end process and architecture. The actually we have to close all the loops. If is started here, if you have to close, process is here, process you have to close, then architecture you have to close. See, mux 4 is successful. Compiler is showing successful result. Now let us see the work part. You have to search for mux 41. Mux 41. It is mux 41. Okay. Instant part. You have to edit all the items in the region. And mux 4 here. Yes, selection input fine. These are the C I is input and S is output. Let us take this input as 1010. Suppose I am taking 2 as a clock of 100 PS, right? 2 as a clock of 100 PS, and mux selection input 2 is 10. Okay, now I'm simulating. See here, when selection input is 10, 10 means when selection input is 10, this is your output. 10 means you have, it is mux 4. At 10, y is replicating I2. Now see, at 10, y is replicating I2. Try to see this array. Here I2 is in the clock form. Now try to match this I2 with output. They are matching. They are matching. Now suppose I'm changing here I equals to, I'm just changing S to 0 1. See the changes. See, it is 1 here. Now S is 0 1 means this I1 is replicated to the output. That's why y is 1 here. Y is 1 here. So this is the output. You can better revise. You can program it. You can code it, and if you have any problem, you can raise the problem to me. I will try to get rid of that. So closing this simulation in the same way, else if condition also work. That is a case condition also works. See, in case condition, what you have to do in the same way, you have to take the process statement, all the uh, event, all the inputs where event are taking place, where changes are taking place. You have to include all the such a statement within the process and selection input. Then see here, case is applied on selection input when SCL, that is when S is 0, 0, then Y is this. You have to imply, you have to see in if else condition, it is written when if SCL is 0, 0, then Y is less than equal to A. Here it is written as when 0, 0, then Y is less than equal to A. So let us change the statement here. Within the same program, we are changing. It will work also. Here, what we're doing, let us change the program underscore C case statement. There's underscore C case statement. Uh, Let it be case S is. Case S is when 0, 0. Then you have to write implies Y less than equal to I of 0. Then is colon when 0, 1. It implies Y less than equal to I of 1. Similarly, when 1, 0 implies Y less than equal to I of 2. When 1, 1 implies Y less than equal to I of 3. Then is close the colon here. And case and process and architecture. Save it. Let us compile. It is saying one error. And case when others. Actually, you have to write other statement also. For else condition, y is less than equal to colon, it is 0. Then is colon is closed. Let us simulate it again. Case statement 27 is their case as is. There is one error near the case. Actually, one began has been used as in the if else condition, and there is need of two began. So after process, there must be begin again. I think it should work now. Yes, it is working now. The mux 4. It is not mux 4. Find mux 4 within the same program. I have it is 4 1. Name is 4. File name is 4. We have to select 4 1 for simulation purpose. 4 1 C case. Add with all items in the region. Then is this is forced. Let us take 1 1 1 0 or 0 0. Case S is 0 1. Let us see what is the output. C for 1 0 0. Let us see the statement. 3 is 1, 2 is 1, 1 is 0 and 0 is 0. And let us see case that is S statement. It is 1, it is 1, and S1 is 0 and S0 is 1. So what is Y? Since it is 0 1 means 1 is selected, it is 0, output is also 0. Suppose I'm changing this as a clock, same is reflected. Let us see is it reflected or not. If it is reflected means our output is okay. Yes, it is a reflecting one. You'll see it is reflecting one. If I'm making it 0, suppose force and suppose forcing this to 1, and partly I will change it here. Force it is 1 1. Then I'm changing here, so you are getting it is 1 1. So 3 is 1 here. That's why for 1 1 case, y is 3. Y is 3. Whatever 3 is written, y is 3. The above part actually it is of 4 bit. That's why it is appearing as a bus. It is appearing as a bus. 1 1 0 0. This is appearing as a bus. So For today, this much only. From tomorrow, we will try to learn counter and register. Thank you. Thank you.